Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 28. We're in lecture 13. We're doing part 6 of sufficient statistics. So we're going to be talking about multiple parameters and the Rao-Blackwell theorem in this video. We might discuss some of the supplemental material as well. So last time we talked about the some details and nuances of when with the factorization theorem, and when we maximize L of and the MLE, when we maximize the MLE or the likelihood function, the only term that contains theta is phi. So we maximize phi, but phi is a function of x only by this sufficient statistics. Therefore, if there's a unique value of theta that maximizes phi, then it must be a function of this. So in other words, the MLE is a function of the sufficient statistic, okay? So the MLE is always a function of the sufficient statistic. So many times we have more than two parameters. We'd have the binomial. You say, well, that just has p. No, it has binomial n and p, and we can maximize n, we could maximize p, so those could be parameters as well. The negative binomial has r and p, and then the beta has alpha beta, gamma has alpha beta, the normal has mu and sigma squared. So we can extend these methods that we've learned so far to the new situations for multivariate parameters. So here's our multivariate factorial or factorization theorem. Let x1 to xn denote the random variables with a joint PMF or PDF, f of x1 to xn, theta 1 to theta p, which depends on parameter theta, which is the vector of these, theta 1 to theta p. Okay? So the statistics u1 of x1 to xn, u2 x1 to xn, up to u sub p of x1 to xn are jointly sufficient for theta 1 up to theta p, if and only if the joint PDF or PMF of x and theta is equal to phi of u1, u2 up to up, and theta 1 up to theta p times, this is a times, h of only x, x1 up to xn, where phi depends on x1 up to xn only through or by these functions, these sufficient statistics, and h does not depend on any theta sub I for I equals 1 to p. Okay, so this is our extension of the factorization theorem. Now, what I believe really happened is I believe that the factorization theorem was made for all parameters, and then special case is one parameter, but don't quote me on that. So let's do example 5. We're going to do the most important example that we can. Okay, sorry, I was looking at this little dot here thinking it was on my screen, but it's in the paper. Okay, so let x1 to xn denote a random sample from a normal distribution with mean mu and variance sigma squared. So theta 1 is going to be mu, theta 2 is sigma squared. Again, this is a nice trick to use because this substitution keeps us from having to go d sigma squared and not, or actually we're not doing an MLE. If we're doing an MLE, it's really handy to do this substitution to keep the differentiation straight when we're wanting sigma squared and not sigma. So find jointly sufficient statistics for sigma 1 or theta 1 up to and theta 2. We only have two of them. All right. So the first thing we need to do is write the PMF of x sub I, the individual PMF of one random variable, and we're going to say theta 1, theta 2. Now you could just say theta and say theta equals theta 1, theta 2 as a vector, but so that's up to you. okay, for the notation here, at least. So this is going to be 1 over 2 pi theta 2 under the square root, because remember theta 2 is sigma squared, and we only have sigma there. But this makes it nice in that we have theta 2, not the square root of theta 2. We don't want to deal with that. And then we'll have exp, and we have negative xi minus mu quantity squared over 2 theta 2. So mu, oh, I need to switch out, mu is theta 1. So let me erase this. So negative x sub I minus theta 1 quantity squared over 2 theta 2. Okay. And then we need the joint PDF, x1 up to xn, theta 1, theta 2. And so that's going to be the product of this. And so I can write that out just for the sake of doing it, which will be, I'm going to change this to 2 pi theta 2 to the negative 1/2. A square root is a 1/2, and if it's in the denominator, then it's a negative exponent. So changing it to exponents is really a good idea here. And then I have exp, and I can do negative 1 over 2 theta 2, and then I can do x sub I minus theta 1 quantity squared if you like. You don't have to write it that way, but I like to write it that way so I can see what's happening. Or actually, I don't like to write it that way. I like to write it as a fraction, that's right, so that I see that I have the common denominator. So I have negative x sub I minus theta 1 quantity squared over 2 theta 2. All right, so I have a common denominator, 2 theta 2 here. And so when I do this, I get these are constants here. They don't have any subscript I in them. So I'm going to end up with this n times. So I'm going to end up with 2 pi theta 2 to the negative 1/2 raised to the nth power, right? And when I have that, I multiply these exponents. I'm going to change back to blue. It's a little nicer. So I end up with 2 pi theta 2 to the negative n over 2. And then I have exp, and I have the negative sum of xi minus theta 1 quantity squared over 2 theta 2. Okay. And what I'm going to do is I need to do a couple of things. First, I need to make this, well, I don't have to, but I'm going to put this into the exponent, the exp. Why? Because this is a exponential family, it's going to be a lot easier to find this, but I want theta together. So we'll do this. We'll make this exp, and this will be log of 2 pi theta 2 to the negative n over 2 minus, and now I'm going to expand this, and so I have negative sum of xi squared minus 2xi theta 1 plus theta 1 squared. Okay, all of that inside of here. And I can rewrite this. So I have exp, that's e raised to the, and this will be negative n over 2 log of 2 pi theta 2. And then I'll have minus, and I'll have 1 over 2 theta 2 times the sum of xi squared minus theta 1 sum of 2xi plus the sum of theta 1 squared. Okay. And so what I can do here is I can rewrite this as exp negative n over 2 log 2 pi theta 2 minus 1 over 2 theta 2 sum of xi squared minus 1 over 2 theta 2, and this can be theta 1, and there'll be a 2 sum of xi plus, or so this was a plus, so I had a minus here. I have to take this and distribute. That'll be a minus, that'll be a plus, this will be a minus. So keep the sign straight, or else you end up with a mess. And so we have this quantity here is n theta 1 squared. Okay. So this is n theta 1 squared over 2 theta 2. And let's make sure that we have this right. So we have n over 2 here. This term is good. And then I have this term is good, negative. And then I have these twos cancel, so this term is correct. And then I have this term, good. And, okay. So now, everything, so this is phi, and I can say times 1, and 1 is going to be my h of x1, x2, up to xn. And, well, before I do that, I can just say that, and then, oops, equals exp, and I'm going to simplify. I'm going to have, and I'm going to rearrange a little bit so that I have, well, it doesn't matter, n over 2 log 2 pi theta 2 minus 1 over 2 theta 2 sum of xi squared plus theta 1 over theta 2 sum of xi minus n theta 1 squared over 2 theta 2 times 1. This is h, and this is phi. And so u1 is going to be what goes with theta 1. And so I have so theta 1 is sum of xi. That is right here. Okay? And theta 1. So this is the only time that we have x and theta 1 together. Okay? Here I have theta 1, but it's with theta 2 and nothing else. Here I have theta 2 with some other constants. And here I have theta 2 by itself with the sum of xi squared. So I'm going to call this y1 equals sum of xi, and y2 equals the sum of xi squared. And so, and then I have theta 1, theta 2. So I have phi. Let's see how I wrote this. Yep. That and theta 1, theta 2. Okay. And so, therefore, y1 equals the sum of xi, and y2 equals the sum of xi squared are jointly sufficient for theta 1 and theta 2 respectively by the multivariate, MV is multivariate, factorization theorem. Okay. Now, I can also say, I ran out of room, so also x bar equals 1 over n y1 and s squared equals n sum of xi squared minus sum of xi quantity squared over n minus 1, which is equal to ny2 minus y1 squared over n times n minus 1 are also jointly sufficient for theta 1 and theta 2 because x bar is a 1-to-1 function of y1 and s squared is a 1-to-1 function of y2. So y2 equals n minus 1 s squared plus 1 over n y1 squared equals n minus 1 s squared plus n x bar squared. And y1 equals n x bar. Okay, so those are the one-to-one functions that we have there. Okay, and if you remember, those are functions of our MLE that we found. Okay, so the important point to stress is that if a sufficient statistic exists, then once the sufficient statistics are given, there is no additional information about the parameters left in the conditional distribution. In other words, all inferences should be based on the sufficient statistics. This is a key point. Okay. Now, let's talk about a very famous theorem called the Rao-Blackwell theorem. So let x1 to xn be a random sample from a distribution with PMF or PDF f of x theta, where theta is in sigma, which is the parameter space. Let y1 equals u1 x1 up to xn be a sufficient statistic for theta, and y2 equal u2 of x1 xn be an unbiased estimator of theta, where y2 is not a function of y1 alone. Okay? Then the expected value of y2 given y1 is equal to some value is u of y1 equal u's of y1 defines a sufficient statistic u of y1, which is first a function of a sufficient statistic, 2 an unbiased estimator of theta, and 3 has a variance that is less than the variance of y2. So u of y1, the variance of u of y1 has to be less than the variance of y2. Now, the proof there is in the book. So if you'd like to see that proof, then by all means, look at the textbook. Okay. So this theorem shows that for every unbiased estimator of theta, this is the idea. So you know, looking at the theorem, it may seem pretty complex. So let's talk about the general idea. This theorem shows that for every unbiased estimator of theta, we can always find another unbiased estimator based on the sufficient statistic that has a smaller variance than the original or first unbiased estimator. And you see the equal to sign there, so if it's the best, you can, then you can find a function of it which has the same amount. Okay. So an unbiased estimator that's based on a sufficient statistic is better than one that is not based on a sufficient statistic. So that's important to remember. We should start our search for an unbiased estimator with the smallest variance and MSE, which is equal to, if it's unbiased, then the bias is 0, right? And so the MSE would equal the variance. So MSE equals the bias squared plus the variance of the parameter. So we should start our search for an unbiased estimator with the smallest variance by considering only those that are based on a sufficient statistic. Now, if a distribution is a member of the exponential family and an unbiased estimator exists, there is only one function of the sufficient statistic that is unbiased. In other words, the unbiased estimator is unique, but it's only for an exponential family and an unbiased estimator. So there's only one function of that sufficient statistic that is unbiased. Therefore, the unbiased estimator is unique. So those are all ramifications of this Rao-Blackwell theorem, which makes it very important. Okay. Also, for a sufficient statistic y for theta from an exponential family distribution, if another statistic z has a distribution that does not depend on theta, then y is independent of z. Now, this last property is the reason that we have z is equal to n minus 1 s squared. That is independent of y equals x bar when the sample is from a normal distribution, not from other distributions, but just from the normal distribution. Okay? The sample mean is a sufficient statistic for mu, and z n minus 1 s squared, which is equal to the sum of xi minus x bar squared, has a distribution that is free of mu. To see this, we have to find the distribution of z. Okay? So to do that, it's a proof. So we're going to use the MGF of z. Okay? So we have E of e to the tz is equal to, now we have all these parameters, and so for every parameter we're going to have we have all these random variables, so for every random variable we have an integration, negative infinity to positive infinity, negative infinity to positive infinity, dot, 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 negative infinity to positive infinity, and we have E of tz, which is the sum of xi minus x bar quantity squared, times 2 pi sigma squared to the negative n over 2 exp, the negative sum of xi minus mu quantity squared over 2 sigma squared. Then we have dx1, dx2, dot, 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 dxn. Let x sub I minus mu equal wi for I equals 1 to n. So we're making a substitution. Then x sub I equals wi plus mu, okay? And then x bar equals 1 over n sum of xi, which is equal to 1 over n sum of wi plus mu. We're substituting in for x sub I, which now we're distributing the summation 1 over n sum of wi plus n times mu. Mu is a constant, so when we sum it up n times, we just get a n of those. And this is equal to 1 over n sum of wi plus mu. Okay? Now, x sub I minus x bar, that's in this, where is it? That's in here, right? So that's going to equal wi plus mu minus w bar. So we're calling this, so I'm going to say this is equal to w bar plus mu. And so then I'm going to substitute that in, w bar plus mu. Okay? So that is x sub I minus x bar, which is equal to wi plus mu minus w bar minus mu, which is equal to wi minus w bar. So the mu's canceled here. And d sub xi is equal to dwi. Okay? So dxi is, so here is xi, so dxi is just going to be, this is a constant, so that goes to 0 when we take the derivative. We just end up with d sub wi. So if xi is equal to negative infinity, this implies wi is equal to negative infinity. If xi is equal to positive infinity, then that implies that wi is equal to positive infinity. So we keep the same limits. Therefore, e of e to the tz is equal to, I have negative infinity to positive infinity, negative infinity to positive infinity, dot, 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 negative infinity, positive infinity. And then I have exp, and let's see, exp, and I'm saying t, so I'm wondering where, oh, yes, so we have t from the t here, t times the sum of wi minus w bar quantity squared, okay? And then we have 2 pi sigma squared to the negative n over 2 exp to the negative sum of wi over 2 sigma squared, dw1, dw2 up to dwn. Okay? And this is going to be, let's see, so x minus x bar, I think I forgot a square, w minus w bar, and so the sum of this, okay, so wi, so I've got the sum, so I need the sum of xi minus x bar. Where did I do that? I have this. Yep. So that's going to be, I'm using this. Is going to be the sum of wi minus w bar. And this was squared. let's see. Oh, so this was xi minus x bar u minus mu. Okay, so I need to look at not this, so I'm looking at the wrong spot for the substitution. So I have this quantity here. I have W bar plus mu. That is equal to, let's see, so I have X bar. This is equal to X bar, okay? And Xi minus X bar. So Xi minus mu is equal to Xi minus mu is going to be Wi plus mu minus mu, which is Wi. And so we have this sum of Wi here squared. So that's where that's what we're substituting in to here, okay? And so I left off the square here, and which is a multivariate normal distribution with mean 0 and variance sigma, which is a this is a vector of zeros, and this is a matrix. Okay, so this is a multivariate, and so we have f of w1 up to wn is equal to, let's see, sigma square root 2 pi under 1 to the n exp, yep, to the negative sum of wi quantity squared over 2 sigma squared, okay, where sigma is equal to this matrix where I have sigma squared and zeros on the diagonal and zeros everywhere else. This distribution does not contain mu, does not depend on mu, independent of mu, which ends our proof. Okay? All right, so we've just proved that that z equals n minus 1 s squared has a distribution that is free of mu. Okay? All right. So that's it for this video. I hope that this proof of the of example 5 that showed that z, which was equal to n minus 1 times s squared, has a distribution that does not include mu. So therefore it is it's a 1-to-1. Let's see, so it's independent of that, and therefore it meets our Rao-Blackwell theorem. Okay, so if you have questions, come to virtual office hours. If you need help before virtual office hours, by all means email me. If you're working on a problem and you need help and you want to email me, then email me a copy of the problem, a picture of the problem, so I can see it, because I don't have it memorized and I might not have access to it when you email me, and you don't want to wait any longer than you have to. So email me a picture of the problem and a picture of your work so far, and then I will get back to you as soon as it's possible for me to do so. All right? So please take care of yourself and stay safe, because we want to see you here next time.